Hi guys, this is the Academic Chemistry Intro to Unit 3. So we're going to talk about types of bonds, then we're going to first cover covalent bonds, and then in the next benchmark material, Unit 4, we'll go over ionic bonds. But first it's good just to know that there are different types of bonds. So the bonds that you're learning about aren't the only type of bonds out there. Let's start. Right, so the first thing you need to know is the atom's electronegativity, is its ability to pull an electron from another atom. So I know that's from the last unit, but it's really important to bring it back because it's super, uber important because bonds are involved with electrons. So electrons have to do with sharing electrons. So if you want to know what the bond's going to be like, you need to know who's pulling the electrons more than the other one. Fluorine is the most electronegative element, so it is up here with the electronegativity of 4.0. And 0.7, francium has the smallest electronegativity. So as far as non-noble gases, most noble gases do have an electronegativity of 0 because they don't want to make bonds, so they're not going to try and pull electrons from anyone else. So when you think about that, fluorine is kind of like the bully of the periodic table. Fluorine is going to pull electrons the most. Remember, that goes up in this direction. And francium is like, nah, I don't need your electron. I'm good. Thanks, dude. And so it goes down in that direction. So the type of bond that exists between atoms is classified by where the electrons that are causing the bond are. Like, where are they located between the atoms? So, and this is going to be because of the difference in electronegativity. Are the electrons exactly in between the two? Are they closer to one atom? Are they completely towards one atom and not even shared at all? And that's what determines the bond type. So let's go over an example. First, let's talk about if you have two fluorine atoms, okay? Remember, fluorine is that bully of the periodic table. So here's fluorine, here's both of them, and I did color them differently just so we can identify a few things, but they are the same element. So they do have the same like atomic numbers and properties and all that. So each fluorine has a pull of 4.0. Those are the bully from the periodic table. So we've got an electron here and electron here that are close together, and they're both pulling on each other. So this blue pull causes that. This green pull causes that. And they equally pull. They have an equal strength. So this is called a nonpolar covalent bond. This is seen when the change in electronegativity, that delta sign, that triangle means change, and En is short for electronegativity. So if the difference in electronegativity between two elements is between 0 and 0.39, so the difference between 4 and 4 is obviously 0, then this is a nonpolar bond. Nonpolar means there's no overall pull of electrons. So we know that the electrons are being pulled in two different directions, but those directions actually cancel out, and they're just put in the center between the two atoms. So there's no overall pull in this bond. So if I could draw a picture like this that shows the electron density, the bonding electrons are found equally shared between the atoms in a nonpolar covalent bond because there's no overall pull, so they're equally right in the center. That makes it a nonpolar covalent bond. How about the hydrogen to chlorine bond? So let's talk about their electronegativities. Hydrogen gets pulled by chlorine. So hydrogen's one electron is going to be pulled by chlorine with a strength of 3.0. Hydrogen pulls back with a strength of 2.1. So hydrogen its electron gets pulled over to chlorine, and chlorine's electron gets pulled a little bit to hydrogen. Just a little bit though, not as much. When a polar covalent bond is seen, it's when the electronegativity difference is between 0.4 and 1.69. So polar means there is an overall pull of electrons. If you notice, the electrons are being pulled this way more. They're being pulled towards chlorine more because chlorine is stronger. And then this is called having a dipole moment. So some people just say a dipole moment either way, but the dipole shows the overall magnitude and direction of electron pull. And it's drawn as an arrow with a cross through it. So if we look at this picture, the difference in electronegativity, 3.0 minus 2.1 is 0.9. So that's the dipole we want to show. So it's only relative in size to other dipole moments. So you decide how big you would want a 0.9 dipole to be. And if you have another thing that has a 1.7 dipole, you know, that's going to be almost twice the size. But you decide it's all relative to what you write. There's no official 0.9 dipole size arrow. So if you have a polar covalent bond, the bonding electrons are closer to the more electronegative atom because that atom is stronger, has the stronger ability to pull the electrons. So the more electronegative atom is labeled as having a partially negative charge. So this lowercase delta Greek sign means partial. So you want to label your chlorine as having kind of a negative charge. It's not a full negative charge because it doesn't own that extra electron, but it's got a little more negative than other things. Now, if this chlorine has a partial negative, the less electronegative atom, the hydrogen, is going to have a partial positive. So you can see that the dipole is always pointing towards that partial negative charge and saying the electrons are going that way, and that's what's causing that partial charge. All right, remember how we said dipoles were relative to the size of the pole? So you can kind of see in this picture, we're talking about hydrogen bonded to chlorine, hydrogen to bromine, hydrogen to iodine. So all these have hydrogen, which is 2.1. Chlorine is 3.0, bromine is 2.8, iodine is 2.7. So each of these gets a little less strong for pulling electrons. So you can see that by this red is showing you that electron density. The red is disappearing, right? You even have a little bit of positiveness here. So the dipole moment always points to the more electronegative atoms. So these ones are all pointing towards the right. That might not always be the case, but for this one it is. And the size of the dipole moment is relative to the difference in electronegativity values. So for example, if this is the dipole moment that I draw for HCl, I know that that dipole moment for HBr has to be smaller because my difference in electronegativity is smaller. So the difference in electronegativity here, 2.1 to 3.0 is 0.9, but this is 2.1 to 2.8. So this is only 0.7. So it's a little bit smaller. This is 2.1 to 2.7, so this is even smaller. My scale isn't exactly perfect, but the idea is bigger ones and smaller ones, right? Can you see who has the bigger dipole quickly in whatever picture you draw? Let's look at the bond between hydrogen and fluorine. So we've seen these guys before, talking about their electronegativity. We know that fluorine has the strongest electronegativity, 4.0, and hydrogen only has 2.1. So here are the electrons that they're going to each be pulling on. So hydrogen's electron gets pulled all the way to fluorine, and hydrogen's so weak compared to fluorine. Now, not compared to other things. Remember, hydrogen was able to pull chlorine's electron a bit, but compared to fluorine, it's got nothing. So it can't actually pull the electron from fluorine barely at all. So this is called an ionic bond. An ionic bond is seen when the electronegativity difference is greater than 1.7. So if I look here, my difference is 1.9, so that's an ionic bond. Ionic bonds are made by the attraction of opposite electrical charges when electrons are completely transferred. So this has a big dipole because the charge is fully over on the chlorine. So if I look at this, my fluorine has gained an electron and my hydrogen has lost an electron. And this is called making an ion. So an atom with a charge or something that has gained or lost electrons is called an ion. An anion, so our fluorine would be an anion, is an atom with a negative charge. So I've got a negative drawn here to show me that this is the negative of the ions. And notice ions, ionic bond, okay. So if this guy's negative, we know that this guy has to be positive. So cations is an atom with a positive charge. So we're going to label the hydrogen with a positive. So when you're doing your differences of electronegativity to determine what type of bond you have, this is a handy dandy chart to just take you through spatially which is what bond. So if you have a difference of 0 in your electronegativities, like if you have a chlorine bound to a chlorine or a phosphorus bound to a phosphorus, then you know it's nonpolar because they're equal. And anywhere in this region is nonpolar, no pull. If the difference is between 0.4 and just before 1.7, then it's going to be a polar covalent bond. And if it's over here, it's ionic. On the sliding scale, between 0.4 and as big as it gets, you have a dipole moment possibility. So the ones that have dipoles have to have a difference of electronegativity between 0.4 or greater to have a dipole moment. The smallest dipole would be if it is right here, the very beginning of a polar bond. The smallest polar bond you could have would have the smallest dipole for drawing those arrow sizes. And then at the end, this would be the largest dipole. And then remember, that's all relative to the other dipoles in the molecule of how big or small you draw the arrows. Okay, so here's a bunch of elements, and I want you to figure out what type of bond they have. Remember, you have to do the difference of electronegativity, determine that, well, the bond type, that will determine the bond type. And then also, if it's a polar covalent bond, you need to label the partial positive, partial negatives. If it's fully ionic, label the full positive, full negative. So let's do sulfur and chlorine together. So this is what I'm looking for. Sulfur has an electronegativity of 2.5, fluorine is 4.0, so the difference is 1.5. Now you're going to ignore negatives if you do it in this order because it's just the absolute value of the difference. So since it's 1.5, it's polar covalent, and sulfur is the least one, so that is partial positive, and fluorine is partial negative. So please freeze the video and try and do the rest on your own, and we'll be back to solve them. Okay, so here are the answers for you to check yourself. Make sure you get them right. If not, go talk to a teacher, and I will see you in the next set of notes.